Okay, good morning. Today we are going to discuss about the adaptive equalization algorithm. So what is the need for adaptive equalization? So here the channel, wireless channel is a random and time varying channel. So the equalizer should be adaptive to track the time varying characteristics of the channel. For that we are going for adaptive equalization. We are using some algorithms for adaptive equalization. One is the zero forcing algorithm, and another one is the least mean square algorithm. So what do you mean by zero forcing algorithm? So in adaptive equalizer, the coefficients should be varied based on the channel characteristics. So we are choosing the coefficients in such a way that the zero ISI should be produced by the equalizer. In that way, we have to choose the coefficients. So that is the main aim of zero forcing equalizer. So here we are increasing the number of coefficients. So the equalizer length become infinite and it will produce zero ISI. So the algorithm applied for zero forcing equalizer is, so the channel response or the equalizer response should be inverse of the channel response. In that way, we have to choose the coefficients. Okay, so equalizer response HEQ of F, it should be the inverse or reverse of H channel of F. So that the combined response of equalizer and channel becomes H equivalent of F into HCH of F, it is 1. So what we are observing from this equation, whatever may be the channel effect, it is completely cancelled out by the equalizer. So that we have taken the inverse of channel effect. Okay. So if you are multiplying these two transfer functions, we will be getting 1. So this type of equalizer is called as inverse filter because the equalizer response is inverse of the channel response, so that the name inverse filter. So that is the main objective of zero forcing equalizer or zero forcing algorithm. And the next one is the LMS algorithm, that is least mean square algorithm. So what is the main objective of LMS? So here we are, that is the main criterion of LMS is to make the MSE, that is the mean square error, becomes very, very minimum. So we are going to reduce the mean square error. So that is the main objective of LMS algorithm. So here how do you calculate the error? This is the error we are calculating from equalizer. The error is the actual, that is the desired response minus the actual output of the equalizer. Okay, so what about the desired response? The desired response is the transmitted sequence. What we are transmitting, the same thing we are expecting at the receiver side. So that is the desired response. So this EK, that is the error, can be written as XK minus DK cap. What is XK? XK is the transmitted sequence. So dk cap is the actual output of the equalizer. So xk is the transmitted response or transmitted sequence, and dk cap is the equalizer output. So the error should be minimum. So that is the main aim of LMS algorithm. So what about dk cap? The actual output of the equalizer is the FIR filter response. Actually, equalizer is nothing but a FIR filter. So dk cap is the FIR filter response. So here WNK represents the filter coefficient or weight given to the equalizer, and YK minus N is the delayed response of the input. Actual input of the equalizer is Yn. Okay, so the delayed response of the input is Yk minus N. Because this FIR filter consists of so many delay elements, so the response is Yk minus N. So this is about the actual output. So what is the role of LMS algorithm is? So it minimizes the mean square error. So how do you calculate the mean square error? So mean square error is this one, Ek mean square error, it is equal to expected value of Ek conjugate into Ek. So this is about the mean square error. So we are going to reduce the mean square error by varying the filter coefficients. So for that we are using the iterative LMS algorithm. So in iterative LMS algorithm, the procedure, what is the procedure for iterative LMS algorithm? So every stage the weight is updated based on the error between the desired response and the actual response. Okay, so this is the weight updation algorithm. So Wn of n plus 1. So here the capital N represents the number of delay elements. And small n represents the stage, that is the number of iterations. Okay, so n means nth stage. How many iterations we are taking? N may be 10 or 15, anything we can take. So that is the n is the number of iteration and capital N represents the number of delay elements. So what about the n plus 1? So the weight for the next stage. So the n plus 1 stage weight depends on the nth stage weight. So Wn of n minus this alpha is the step size. So it controls the convergence rate of the equalizer. So what do you mean by convergence? So at one particular stage, Wn of n is equal to Wn of n plus 1. So till that we have to apply the same procedure. So that is the iterative algorithm. So in iterative algorithm, where do we stop? At one stage, W of n plus 1 is same as the Wn of n. So at that time, we can stop the process. So that is the step size. So if you are varying alpha value, you can vary the weight. Updated weight, we can vary. So this is the formula we are applying to calculate the updated weight. So this updated weight we have to apply here and we can vary the dk cap. Okay. So if you are varying the dk cap, what about the error? The error also we can vary. Clear? So the main objective of LMS algorithm is to minimize the mean square error. Okay. So how do you minimize the mean square error? By varying the filter coefficient or weight. So in this way we can vary the error. Clear? So this is the main objective of LMS. So what are the advantages of LMS algorithm? So here we are using the iterative algorithm so that the signal to distortion ratio of this LMS algorithm is high compared to zero forcing algorithm. Okay, then it's a simple program. Using software we can implement this LMS algorithm. Clear? Then what about the drawback of LMS algorithm? It's a slow rate of convergence. Okay, so we can, that is it will not end up with a less number of iterations. It will go up to some 1500. Okay, at that time only we can get W of n is equal to W of n plus 1. So that is the main drawback. Clear? So these two are the main algorithms applied for adaptive equalizer, zero forcing and LMS. Zero forcing is not an algorithmic procedure. Here they are using only this step. That is the H of H equalizer of F is the inverse of channel response. This is the only thing we have to look over in zero forcing. But LMS, it's a step-by-step procedure. So these steps we have to apply LMS algorithm. Okay. So that's all about adaptive equalization. So here based on the channel characteristics, the equalizer filter coefficients are varied. So that is the main principle of adaptive equalization. So next we will see non-linear equalizer. So what is the difference between linear equalizer and non-linear equalizer? So in linear equalizer, the reconstructed message at the output of the equalizer is fed back to the input. So to change the weight. Okay. So to vary the weight of the equalizer, we are using the output of the equalizer. So if the reconstructed message is fed back to the input, that type of equalizer is called non-linear. Then in linear, there is no feedback path. That is the basic difference between linear and non-linear. Okay, so linear means there is no feedback path. Okay, so we are not controlling the input using the output of the equalizer. But non-linear, we are controlling the input based on the output of the equalizer. So there is a feedback path. So the most commonly used non-linear equalizer is DFE. So what do you mean by DFE? Decision feedback equalizer. Okay, what is the principle of decision feedback equalizer? So here the decision on the current symbol is taken. So based on the decision, we are estimating how much ISI the present symbol will introduce in future. So that amount of ISI, first we have to subtract from the input. After that, we have to take the decision for the subsequent symbols. Okay, what is the main principle of DFE? First, we have to take the decision on the current symbol. So using that decision, we have to calculate how much ISI it will create in future. So that amount of ISI, we have to subtract from the input. After that, we have to take the decision for the subsequent symbols. So that is the main principle of DFE. So to implement DFE, we are using two types of filters. One is the feed forward filter and another one is the feedback filter. So using these two, we can implement DFE. So this is the block diagram of DFE. So the input is given to the feed forward filter. Then we are using the decision device. Then that decision is given to the input of feedback filter. Then the feedback filter output is subtracted from the input. Okay, this is about the equalizer output. So this is the block diagram of DFE. Actually, we are using the equalizer at the receiver side. So the input is the received signal. So what about feed forward filter? So feed forward filter and feedback filter both are the FIR filters. Okay. So your actual linear equalizer act as the feed forward filter. Okay. So how many taps in feed forward filter? It consists of N1 plus N2 plus 1. These number of tappings we are using in feed forward filter, because N1 plus N2 delay elements we are using. So number of taps equal to, how do you calculate the number of taps? Number of taps equal to number of delay elements plus 1. Okay, so this is about the tappings used in FFF, that is feed forward filter. Then feedback filter consists of another N3 taps. So total number of taps in the DFE is N1 plus N2 plus N3 plus 1. Okay, so this is about the number of taps in the feed, that is decision feedback equalizer. So what about the expression for feed forward filter? So it's a FIR filter. So the, how do you calculate DK cap? DK cap is the combined response of both FFF and FBF. So the FFF, the response is summation n equal to 0 to, that is here number of taps n1 plus n2. So minus n1 to n2, then Ck conjugate, that is Cn conjugate into Yk minus n. So this is the response of one FIR filter. Plus, what about the response of another one FIR filter? This FBF also another one FIR filter. So the response is 0 to N3. So here Fi, okay, so Fi into, what is the input of FBF? The input of FBF is Dk. The input of triple F is Yk. Okay, so this is the difference. So Dk minus N. So this is about the overall response of DFE. Okay, it's a combined response of both FFF and FBF. So what we are doing, FFF, it's a equalizer. So this equalizer decision is taken. So that decision is given to the feedback path. So feedback path, so many delay elements we are using. So it will give the past sample of the present. Okay. So that past sample we are subtracted from the present. So what we are actually doing, we are subtracting the ISI from the present symbol. Okay, how much ISI it will introduce in the future, that we will calculate. That ISI we will subtract from the present symbol. Okay, so that is the response of DFE, decision feedback equalizer. So why we are preferring non-linear equalizer? Suppose if the channel is highly severe, okay, so that is the channel is highly affected by distortion, so linear equalizer cannot withstand. Okay, suppose if you are using linear equalizer for highly distorted channel, the gain should be high. The linear equalizer should produce high gain, then only we can make use of linear equalizer for highly distorted channel. So that is very, very difficult. Okay, for that we are going for non-linear equalizer. Non-linear equalizer, we can vary the weight. Okay, so no need to apply the linearity principle. Okay, so output, that is the output does not follow the input for non-linear equalizer. So we will not worry about the linearity principle in non-linear. So non-linear equalizer is highly preferred for heavily distorted channel. Okay, so this is a practical equalizer. Clear? So that's all about linear and non-linear equalizer. So we have discussed adaptive equalizer algorithm and non-linear equalizer. So then the next topic is error probability in fading channel with diversity reception. Fading channel with diversity reception. So definitely the error probability of fading channel is high compared to the non-fading channel. So what is the use of diversity? Diversity is used to reduce the fading effect. Okay. So if you are applying diversity for fading channel, definitely we can reduce the probability of error. So that is the objective of this topic. Okay. So how much error we can reduce? How do we reduce the error using diversity? So that we will discuss here. So in fading channel, there are two types of fading channel we are considering here. One is the flat fading channel and another one is the frequency selective fading channel. So flat fading channel, we can reconstruct the so whatever we are transmitting at the transmitter side, that we can reconstruct at the receiver side with minimum probability of error. But frequency selective, we cannot completely reconstruct the information at the receiver side. Okay, so that is the difference. So it's a heavily faded channel. So first we will see the flat fading channel response. So in flat fading channel response, the probability of error is, here we are considering the average probability of error. So SER is the symbol error rate. Okay. So average symbol error rate that we are calculating. So it is 0 to infinity, then SER, SER for particular SNR, gamma represents SNR. So SER for particular SNR into PDF of gamma. So this is the formula we are using to calculate the average probability of error. Okay. So what about this formula? We are averaging the conditional probability at some particular SNR over the distribution of SNR. Gamma represents SNR. So over the distribution of SNR we are calculating. So here you can choose some modulation scheme, any of the modulation scheme we can take. Okay. Then diversity reception, we have discussed MRC, maximal ratio combining, then equal gain combining or selection diversity, any of the diversity we can take. Okay. So you have to choose one modulation scheme as well as one diversity technique. So using these two, we can expand it. Clear? So we can derive the expression. So what we are observing is, if we are increasing the number of diversity branches at the receiver, we can reduce the bit error rate. What about the inference from the derivation? The inference is, if we are increasing the number of antennas or diversity elements at the receiver side, definitely the BER will be reduced. Okay. So normally BER is proportional to nth power of some argument. Okay. So nth power of some argument. So if you are increasing the number of antennas, definitely the BER will be reduced. So that is the main inference from the error probability in fading channel. Okay. So this is about flat fading. Frequency selective fading means definitely both the channel is both time as well as frequency dispersive channel. What about the frequency selective channel? It is both time as well as frequency dispersive channel. Okay. So here we have to analyze or we have to derive the expression in terms of time as well as frequency dispersive channel. So this one you take it as assignment. So assignment number 3 is error probability in fading channel with diversity reception. So you have to look over both flat fading as well as frequency selective fading. Okay, so the procedure is, this is about the expression for average SER. You can choose any one of the modulation and any one of the diversity, either MRC or selection diversity you can take. Okay, then you derive. So this you take it as assignment. Okay, so that's all about the first half of the fourth unit. Clear? So equalizer, linear, already we have discussed in the class, then non-linear equalizer, then adaptive equalizer, then algorithms. Okay, what are the equalizer algorithms? LMS and zero forcing algorithms. Okay, then error probability in fading channel with diversity reception. Okay, so then the first half also we will discuss, that is the diversity. Okay, there are two subdivisions in unit 4. One is the equalizer and another one is the diversity. So we will quickly go through the first half, that is the diversity. What is the principle of diversity? So multiple copies of the same information is transmitted over independent channel. Okay, so that is the main principle, that is the principle of diversity. Why we have to transmit the multiple copies of the same information? So actually diversity and equalizer both are the multipath mitigation techniques. Okay. What are the effects of multipath propagation? There are two effects of multipath propagation. One is the fading and another one is the intersymbol interference. Okay. So we have to cancel out both the effects at the front end of the receiver. After that we can apply further process. Clear? So to reduce the effect of fading, we are going for diversity. Then to reduce the effect of intersymbol interference, we are going for equalizer. Okay, we have to mitigate or cancel out the fading effect. So there are two types of fading. One is the small scale and another one is the large scale. So to reduce the effect of small scale fading, we are using the diversity that is called micro diversity. Then to reduce the effect of large scale fading, we are using the diversity that is called macro diversity. Okay. So how to implement micro and macro? So these two are the general classification of diversity, micro and macro. Okay, again you can apply diversity technique either at the transmitter side or receiver side. Okay. So if you are applying the diversity technique at the transmitter, the name of the diversity is called transmit diversity. Then if you are applying the diversity at the receiver, the diversity is called receiver diversity. Okay. So how to implement micro and macro diversity? Micro diversity is implemented using multiple antennas, and macro diversity is implemented using multiple base stations. So using this concept we can implement micro and macro. Okay. So first we will discuss micro diversity. So micro diversity, what are the different types of micro diversity? Spatial diversity, time diversity, frequency diversity, polarization diversity. So these four are the different types of micro diversity. What do you mean by spatial diversity? So we have to use multiple antennas, then antennas should be properly spaced. Okay. So how do you place the antennas? So that the spacing should create independent path. Okay. So the spacing between the antenna plays a vital role in diversity. So that spacing should provide independent path for the signal. So there should not be any correlation between the antenna signals in such a way that we have to place the antennas. Okay. So every path we should have some uncorrelated signal. Okay. There should not be any relation between the signals. Then time diversity, how to implement time diversity? We have to transmit the information at different times. Okay. So same information we have to transmit at different times, that is called time diversity. Frequency diversity, how do you implement? Same information we have to transmit at different frequency. If you are transmitting the same information over different frequency, what about the spectral efficiency? That is very poor. Okay, because all the frequencies carries the same information. So the spectral efficiency is very poor. So what we are doing is, instead of transmitting the entire information over different frequency, we have to split the information into smaller parts. Then every smaller part is transmitted over one frequency. Okay, that also applicable in frequency diversity. The best example of frequency diversity is OFD. Okay, so the same principle we are applying in OFD. Then polarization diversity, what we are doing? We have two polarizations. One is horizontal and vertical. Okay, so at the receiver we are using two dual polarized antenna to receive both the components, horizontal as well as vertical components. Then we are doing the analysis. Which antenna the signal strength is high? So that antenna is connected to the receiver. Okay, we are receiving both the polarized waveforms at the receiver side, and the best copy is transmitted, the best copy is given to the receiver for further processing. So these four are the types of micro diversity. So first one is the spatial diversity. So there are four techniques under spatial. One is the selection diversity, scanning diversity, maximal ratio combining technique. Fourth one is equal gain combining technique. So these four are the types of spatial diversity. So what is the principle of selection diversity? So selection diversity, the receiver is having n number of antennas. So the receiver is having the n copies of the transmitted symbol. Okay. So from that the receiver can choose one of the best copy. So that is the principle of selection diversity. So we have n number of antenna branches, but only one branch is effectively communicated to the receiver. So other branches are not a part of the receiver. So wastage of resources in the case of selection diversity. Okay. So for that we are going to the next one, scanning diversity. So here it also uses the same principle of selection diversity, but what is the difference? Here every antenna branch is scanned in a periodic manner. So here we have to, so this is about scanning n number of antenna branches. So this is about the receiver. So the receiver will scan one by one. Okay, so here we have the predetermined threshold value. So that threshold value is combined with the, okay, we have the comparator. So from the receiver we are taking the short term average of the received signal that is given to the input of comparator, and another one input is the threshold value, that is the reference value. Okay, so based on the comparator or based on the comparator output, the receiver will connect to any one of the antenna branch. So that is the principle of scanning diversity. Initially the receiver will scan the first antenna. If the first antenna, then every antenna we have to calculate the SNR. Suppose if the first antenna SNR is greater than the threshold value, now the receiver will continue its connection with the first antenna. Okay, so after some time, that is this verification is periodically taken. So after some time the first antenna signal is less than the threshold, then what the receiver will do? Now the receiver will scan the second antenna. Okay, then again the SNR is calculated. If the SNR is greater than the threshold, the receiver is connected to the second antenna. Otherwise the receiver will scan the third antenna. So here what is the difference between this method and the previous method? So in scanning diversity, every antenna will get a chance to communicate with receiver. Okay, so that is the main difference. But in the previous case, only the best antenna is always connected to the receiver. So this is the advantage of scanning diversity. So for the first two technique, one of the best branches connected to the receiver. We are considering only one branch at the receiver side, even though we have used n number of branches. But the next two diversity, we are combining or we are considering all the branches at the receiver. Clear? So n number of branches means all the branches are considered for both MRC as well as EGC. Okay, so MRC means these two are the combining techniques, these two are the selection diversity techniques. Okay, so what is the need of combining techniques at the receiver side? Suppose if the channel is very worst, so at that time the selection diversity will not work out. Okay, so to apply the selection diversity technique, we need some minimum SNR at the antenna element. Okay, every antenna should maintain certain SNR, then only we can apply selection diversity. Suppose if the channel is very worst channel, so the characteristics are highly varied, so at that time selection diversity principle we cannot apply. Okay, because every antenna branch the SNR is less than the threshold value. Okay, so we cannot apply selection diversity. So for that we are applying combining technique. So it's for practical channel we have to apply combining technique instead of selection diversity. So combining technique, what we are doing? We are combining all the branch SNRs. Clear? So if you are combining all the branch SNRs, what about the overall SNR at the receiver side? That is very much greater than the individual branch SNR. Okay. So that is the principle of combining technique. Clear? So what is the difference between maximal ratio combining and EGC, equal gain combining? So the principle of maximal ratio is, so first we have to calculate the instantaneous SNR of every branch. So based on the instantaneous SNR, we have to apply some weight to every branch. Okay, suppose if the SNR is high, so the weight allocated to that branch is high. So weight is high. Suppose if the branch SNR is low, low SNR means less weight. So that is the principle of maximal ratio combining. So first we have to allocate some weight to every antenna branch. So after that it is given for co-phasing circuit. Okay, because every branch the SNR value is different. Some SNR may be positive, some SNR may be negative. Okay, if you are combining all the SNRs without any phase correction, definitely the overall SNR will be very low. For that, we are applying some co-phasing circuit. Okay, co-phasing we have to apply. After that, we have to combine the SNR. Okay, so that is the principle of MRC. So we have to calculate the weight, then we have to apply the phase correction. After that, we have to combine all the branch SNR. So here in MRC, the overall SNR or the total SNR at the output of the diversity is summation I equal to 1 to m gamma I. We are using m number of branches. So every branch, the instantaneous SNR is gamma I. If you are adding all the branch SNRs, you can get the overall SNR of the branch. So this is about MRC. The next one is EGC 1140 overall. So in EGC, the principle is same as MRC, but there is no weight. That is, here the weight is uniform for all the branches. But here every branch different weight. Here all the branches are having unity weight. Okay, so that is the principle of EGC. So these four are the different spatial diversity techniques. So that's all about the today's portion. Okay, so the assignment question is error probability in fading channel with diversity reception. Okay, thank you.
So good morning. Let us look at the topic diathermy today. So first of all, we should know what is known as a diathermy. So diathermy is nothing but that is through heating. That is by applying the heat, many diseases can be treated. Even it is not diseases, it can be any swelling and then pain. Those things that we can able to treat just by applying a heat. So through heating, if anything can be